Okay, so in 4.2, we're going to do some more function analysis, but we're going to focus on not so much theorems, but where the original curve would be increasing or decreasing. We will also learn the first derivative test and some other vocab words that are going to be important for you to recognize and memorize. So you can go ahead and read this paragraph. But the whole idea is that we want to use calculus to use our derivative rules to analyze the original function. Most of these problems you would be doing without a graphing calculator. So you should know some information about the curves, but we're going to strengthen that and show how we can use math to find it. So some of the terms we want to define so we understand when I say these words what they mean. So a function refers to the original. It's increasing when the y values are getting larger. Okay, so we can tell that on a graph. So if you look over here from b to infinity, because we write everything in interval notation, the y values are getting larger, and you always read a graph from left to right. So if you have not been using interval notation with the parentheses and brackets, if you've been using the inequality symbols, try changing over to interval notation. Okay, I can help review it with you as you need, but I will use it every day in the rest of the course. A function is decreasing when the y values get smaller. Okay, so there we go. And like I said, when you read it from left to right. And then constant. So right there in the middle. A lot of our curves will not be constant for very long, but we still define it because you might be given some graphs and asked to write intervals. Okay, so we're going to discuss an idea. So I've got 3 different graphs here. And so we talk about increasing curves. There's 3 different varieties, and it's really about the shape of the curve. But notice the y values on all 3 do get larger from left to right. So if we look at all 3 of these graphs, what is true about the slope of the tangent lines, which remember, slope of the tangent line refers to the derivative in increasing curves. So what I'm going to do is I'm going to draw the tangent lines. Well, what I know here is that my slopes are all the same. Here, my slopes actually get steeper. And here, my slopes get smaller. Because the flatter you get, the smaller the slope value is. So, well, we need to, these don't have a pattern, like they're all 3 different things. So we need to notice something else. So if we just take it down to the basics, there's something else that we can notice. So even though these are equal, these numbers get bigger, these numbers get smaller, they're actually all positive slopes. So the slope, so they're all positive, okay? Now, let's look at my next. So then we look at decreasing functions. And so we'll draw these tangent lines. So these, the tangent slopes, are the same. These, as we go, it's kind of hard to tell, but like that, and then this. So these are kind of getting flatter, and then these actually get steeper. So these are getting smaller slopes, and these slopes are getting bigger. Not by much. So once again, our patterns aren't the same, but if we look at the actual value, keep it simplistic, because they're going from left to right, they're going down, these are all negative slopes. Okay? So then that leads us to a generalization. If these are the only scenarios, and this is what happens, and this is true, then we can come up with some rules. So that is the first thing that we want to memorize and make the connection between. So if f is a function, it does have to be continuous on the closed interval and differentiable on the open interval, just as all the theorems were. So you'll see this on every single rule that we usually use from now on. Then we can say 3 different statements. We can say if our derivative is positive, for all x on the open interval, then the original function is increasing on the same interval. Okay, so notice if the derivative is positive, that means the original y values are increasing. Okay, so you be very clear in your notation and your words, because if you don't say that clearly, it's incorrect. And these would be justifications on a free response question. Okay. If your derivative is negative, then the original function is decreasing. If your derivative is 0, we saw that back in the theorems, then it means that your original function, the y values are the same. Okay. So we knew when our derivative was equal to 0, that was a max or a min. And so you can have max or a min over an interval if the graph is given, not usually if you're given the function. Okay, so let's talk a little bit more about parentheses and your interval notation. Okay, so I always like to tell my students that we know things used to be exact, things are right, things are wrong. We have to watch our notation, things like that, except when we talk about intervals of increasing and decreasing, okay? There's really a big debate in the math community to whether or not you can increase or decrease at an endpoint, because that's where you're starting and stopping. So whether or not you use brackets or parentheses, they're basically telling you that the AP College Board is going to accept both of them, okay? So I do try to stick with the notation of the rules, but I don't look at your answers for that, just so you know, okay? They're all acceptable. They do not make a distinction to whether one's right or wrong, one's wrong, okay? In all my explanations, I will make sure I clarify it though, so you understand what most of the math community thinks. Definition, critical value. This word gets misused a lot. So it's really important to remember this definition, okay? So a question might say, state all the critical values. I will use this word critical a lot, and I always use it appropriately. If you use it inappropriately, you might still get the right answer, but I just don't want to have any confusion. So I will only use it when it's defined to be used. So a critical value is a value of x, okay, where the derivative is either 0, a horizontal tangent line, or it does not exist. So you have a vertical tangent line. This part got left out, okay? So that is by definition. It's called critical. I will refer to other words as important values, but not the word critical. Critical has its own special definition. So typically we want to find the critical values. It's the first step when you want to find intervals of increasing and decreasing, because you need to know where am I going to change from my function increasing to decreasing. So if you notice on a curve, well, here we are decreasing and then we are increasing. So there's one spot where there would be a horizontal tangent line. Same thing, if we go from increasing to decreasing, there's a horizontal tangent line right there, okay? And so that's where our derivative was equal to 0. So critical point is equal to 0 or does not exist by definition, okay? And remember, a derivative would not exist when you take the derivative and then you get an undefined value. So you should have a denominator or a domain restriction like a square root, okay? All right, I have 2 examples, and then on your homework, you have a bunch of examples because we're reviewing derivatives, we're reviewing solving, and we're also showing some different scenarios. So your homework will be longer than the notes, okay? All right, so number 1, find the intervals for increasing, decreasing, and constant. Now, I didn't formally write it out, but typically all calculus teachers and AP readers want to see your work organized in a specific way. So I'm going to show you how to organize this. And I didn't write this out as rules, but it is the rule, okay? So first thing, if I want to find intervals of increasing, decreasing, or constant, what I mean is I need to know what I'm looking for. So I want the derivative to be positive, the derivative to be a negative value, and constant means my derivative value is 0, okay? So step number 1 is to actually find the derivative. And you want to show that in like the box of the free response. And these are typically nice to do. So 12x minus 3x squared. Now, I'm going to label it, but we always want to find the critical numbers, okay? because that's where our function can change from increasing to decreasing. So we're going to take our derivative and we set it equal to 0. I don't have a denominator here, so there would not be any values where my derivative is equal to 0. We're going to factor. So I'll common factor 3x. So 4 minus x, zero product property. So x equals 0 and x equals 4. Now, the way we organize our information is on a numbered line, okay? If you create good habits in this section, it's going to make the next section easier. So I'm going to label this as f prime, all right? Because I'm going to make, this is called a sign chart, S-I-G-N. Now, a sign chart alone on a free response question is not enough to earn the points for a justification, okay? They do want to see it organized because you can show your work, but then you will have to write a written statement that kind of puts everything together, all right? So they're very specific. This was about 15 years ago, that sign charts need to be explained, but they do want them. So what we want to do is we want to label the critical points. So step number 1 is find, we'll say critical points, critical numbers. Step number 2 is we want to make a sign chart and you want to label it. So we want to label the critical points, so critical numbers on it. So I got 0 and I get 4, okay? And we don't draw any other notches, just so you know. You only label the critical points. Now, what we're going to do, we call it a sign chart because we just want to know the signs of the derivative on these intervals. So there's one interval from negative infinity to 0, another interval from 0 to 4, and then from 4 to 0. These are all the same signs. Mathematically, we found the only places where our signs could change, okay? So that's why if I pick any number over here, they will all be the same sign, and any number in the middle, and any number on the right. So we need these dividers to help organize our information, okay? So as long as you solved correctly, you can pick any number on the intervals. So what I do is, you don't have to tell the reader, but I'm going to tell you, and I draw in parentheses. So I want to pick any number that's smaller than 0. So I'm just going to pick -1, just because I want to. And you'll be doing this by hand. What I want to do is I want to find what sign is my derivative, because this is a derivative sign chart. So you take that -1 and you want to plug it into your derivative, but pick the easiest one because you don't care about the number, you just care about the sign. So I'm going to pick this version right here. So in my head, I would do 3 times -1 and then 4 minus -1. And I just want to know if it's positive or negative. So I just know, well, 3 times a -1 is a negative, and 4 plus 1 is a positive. So a negative times a positive gives me a negative number. So I just draw a negative. And that means all the x values if I would plug it into my derivative. But notice how, see, I didn't just plug it into the original derivative. You plug it into what you can get the fastest. And I didn't even do the values because that's irrelevant. All right. Then we go in the middle. So you pick any number between 0 and 4. So you can't use 0 and you can't use 4 because our value of the derivative is 0. So I'm going to pick +1. So same thing. I'll plug it in right here. So 3 times 1 is positive. And then 4 minus 1 is also positive. So positive times positive is a positive. And then I pick another number that's 4 to infinity. So I just picked 5. So then I would pick 5 right here mentally. So 3 times 5, well, that's positive. 4 minus 5, that's a negative. So positive times a negative is a negative. Okay, so this is my sign chart. Now in words, what I like to do on my sign chart is I write f of x, and then I interpret this. So remember, our rule said if our derivative was negative, it meant my original function was decreasing. If my derivative was positive, it meant my original function was increasing. And if my derivative is negative, so decreasing. Okay? So notice how my sign chart is for the derivative, so they're positives and negatives. In light blue, I've interpreted what my original function y values were doing. That is a very clear distinction you need to understand. A visual, because I think the visual helps, because we'll ask other questions, is I sketch it. And I just sketch it like down here. So if I know my function is decreasing, I just go, we decrease until we get to here. Then I increase, and I don't care what my y values are, and then I decrease. And so this is a kind of a rough sketch of what my original function could look like, because then it's visually easier for me to see some things. So they wanted our intervals. So we always use interval notation. So for increasing and decreasing, I always use parentheses. So it's always the lowest x value to the highest x value, okay? So I'm going to do this in black. So I would say increasing, we're going from negative infinity to 0. In union with 4, I gotta change that. We're decreasing, sorry. So we're decreasing from negative infinity to 0, and we're also decreasing from 4 and on to infinity. We're increasing from 0 to 4. We're not constant ever, so I don't even write that on my write-up, okay? So now what's going to happen is we might find extrema, which we are, okay? That's the next part. All right, so there is a connection. Okay, let's do my second example. Like I said, these can be any derivatives that they want. So here I get f prime. It's a quotient rule. So I get low d high minus high d low all over low squared. I'm going to clean this up. So distribute a negative 1 all over this. So those cancel. I get 8 over this. Okay. Now for critical, it's where our derivative equals 0 or undefined. So undefined is when our denominator only equals 0. So if we want to solve this, I can put that over 1, and then we can cross multiply. So 0 times that is 0, 1 times 8 is 8, and a number equals, that's false. So what that means is this doesn't give us any solutions, okay? And so what that means is I don't have any value that makes my derivative equal to 0. For undefined, I'm going to take the square root. So x plus 6, square root of 0 is 0, so subtract 6. And this was a domain restriction anyway, so if I didn't check for undefined, I would need that anyway because that's when my derivative has a domain restriction. My original function has that restriction too, so notice that's the same, and that is critical. So on my sign chart, I only have one critical number. This is my derivative. I always like to label the sign chart because eventually you're going to have more than one. So you need to know which one's which. Okay, so when you go to test your derivative, you want to plug it into something that you wouldn't have solved already. So I'm going to use this for my sign chart, just for the signs. Okay, so I can test any number smaller than -6. So I'm just going to try -8. So I have a positive on top, and then if I plug in -8 plus 6 squared, it's going to be positive. So this is positive, my derivative. And I can pick any number. I like to pick 0 that's bigger than -6. So it's positive on top always. And then 0 plus 6 squared is also positive. So what this means is, let's get my blue out. My original function is increasing and increasing. So I'll say increasing intervals from negative infinity to -6 and -6 and on. And so some people say, well, what about at -6? Well, -6 really isn't in my domain, so it's not increasing or decreasing. It's a whole, so it really doesn't exist. So you really don't want to say from negative infinity to infinity if you don't have to. If that's your only multiple choice answer that's possible and these two aren't there, then you can, okay? So what happens is there's a word when something goes from increasing to increasing or decreasing to decreasing and it doesn't change signs. They also call this a stationary point. Stationary point. Typically it's defined though, so I do like to keep mine separately. So for decreasing, I would just write none. So visually, what's happening is we're decreasing, and it can be in a curve. We have a hole, and then we're decreasing. So we have a hole because this isn't defined on our original function, okay? Okay, so the next thing is a pretty important test. It's called the first derivative test. Okay, so the first derivative test says that, here we go. If you have a critical value, so you do need to set your derivative equal to 0 or undefined, and that's the only place that this could happen, and it is continuous on the other interval, okay? So if your function is differentiable on the interval, except possibly at c, like our last value was, then our y value can be classified as the follows, okay? So it does have to be defined on the original. So if we went from, our derivative was negative, so if we go from decreasing to increasing y values, what happens is you actually, at that critical point, you have a minimum, okay? And that's where our derivative is equal to 0. If our derivative was positive, so our y values were increasing, to our derivative is negative, so our y values are decreasing, then we actually end up with a maximum. If my derivative is the same sign, so we go from a positive derivative to another positive derivative, and it's defined, then that's not a max or a min. So that's what we call a stationary point, okay? It's defined on the original value, so we classify it as a stationary point. It's also critical though, okay? So you don't have to change signs. Most of the time your function will, but there are always going to be exceptions. And these exceptions happen a lot just to make sure you are doing your test and you're not just assuming they change signs. Now, we talked about relative or local extrema. So relative or local, those are the same words, and it just means in an overall region, here's a picture again, it is the highest or lowest point. So the absolute maximum is also a local max. It gets two words. The absolute is the best word though, okay? It implies that it's also a local. So same thing with a relative minimum. These can happen at endpoints or they can happen within an interval. But see how this one also has relative and local. So in an overall area, it can be the highest or lowest. These rules up here, they can apply on your sign chart to classify as maximum and minimums on endpoints if you have them. It really depends on your function. Notice this rule doesn't tell you what the maximum or minimum y value is. It just tells you that it is a max or a min, okay? So, there we go. So let's try the first one. So this says find all the relative extrema, so that's max and min, of this. So notice I'm going to use kind of the same steps here, and this green curve is actually going to kind of help me visualize and answer the question. So first we need to find the derivative. So f prime, these are nice power rules. We want to find our critical value, so I always like to label it. So 0 equals this. We want to do factoring. So common factor 20x, so we're left with x squared minus 2. And we set those equal to 0. So divide by 20, add 2, take the square root. Okay, so on a sine chart, this is my derivative. We're going to label them. So we have 0, we have negative root 2, and we have positive root 2. And then this is what I'm going to use, because I just want to know if they're positive or negative. It's hard for me to tell on the original without a calculator that you would not have. So I need to pick any number that's smaller than negative root 2. Well, negative root 2 is bigger than 1, so I'm just going to pick negative 10. Okay, so if I pick negative 10, I have a negative times, well, negative 10 squared is 100. 100 minus 2 is a positive. So negative times positive is negative. Then I have to pick any number between 0 and root 2. Well, I know root 1, which is smaller than root 2, is 1. So that's what I'm going to pick. So negative 1. So negative times, well, negative 1 squared is 1. 1 minus 2 is negative. So a negative times a negative is a positive. Same thing here. I'll try 1. So 20 times 1 is positive. 1 squared times, minus 2 is negative. So positive times negative is a negative. And then I'm going to pick 10. So that's positive. 10 squared is 100. 100 minus 2 is definitely positive. Okay? So that meant our original is decreasing, increasing, decreasing, increasing. With polynomials, they usually alternate. With other functions, you just never know. So if I want to find the relative max or min, I don't remember all those rules, but if I draw it, I'll be able to see. So if I decrease, I'm going to make my y value go down. Then I increase. Then I decrease. Then I increase. Okay, and so that's the shape, generally. So then I can see oh, well, I keep going and I keep going. So those are not extrema, but I have a minimum, and I have a maximum because it's a high point. And so then I just say min at this one, x equals negative root 2, and we had one over here at positive root 2, and a max at x equals, it was at 0. If they want the point, you would have to take these x values and plug them into the original to find the y value. Typically, because of time, they just want the x value. Okay, so that's the first derivative test. The sine chart classifies increasing and decreasing. The first derivative test classifies max and min. All right, and so if you had to justify a max and min, it would just be that. I would say there's a max at x equals 0 because at x equals 0, f prime of x goes from positive to negative. That's it. You're really just saying what the signs are. All right, find relative extrema, and I just wanted to pick a trig one for the solving aspect and sine chart. So our derivative, well, cosine's continuous, 1/2 x is continuous, so continuous plus continuous is a continuous. So we get, and because of this cycle, they just limit our domain. So our derivative, cosine is negative sine, plus 1/2. We want to set that equal to 0 to find our critical values. I always like to label things in case that's what the question is asking. Add sine. So now we need to solve this without a calculator. So this is asking you what angle has a sine value of 1/2. So you have to remember your special triangles. This was a 30, 60, and then there's 45, 45, 90. So 1, 1, root 2. Across from the 30 is 1, across from the 60 is root 3, and the hypotenuse is 2. So sine is opposite over hypotenuse. So I need to know which angle has the opposite side 1 and the hypotenuse 2. So we're looking at this triangle. So the opposite side of 1 and the hypotenuse. So that means 30 degrees. So we want to use 30 degrees. But now we need some trig review. So sine, all students take calculus. So we need a 30-degree reference angle. So I've got 30 degrees, so they're all positive here. The sine is positive, the tangent is positive, and the cosine is positive in these quadrants. So we want 30 degrees here, and then sine is also positive in the second quadrant. So I'm going to draw another 30-degree reference angle, because 30 degrees is the angle that has a sine of 1/2. So then I need to find those angles. So this is 30, and we're going to convert to radians in a second. And then this one is really, this is where we stop. So I want to go all the way to here. So remember, half of a circle is 180. So I want to take that 30 off. So 150. Now, all of your answers will be in radians. So to convert, we've got 30 degrees, and we always multiply by 180 on bottom is the same as pi. So 30 goes into 180 6 times. So this is pi over 6 as radians. Same thing for 150. So I get pi over 180, cross out the zeros, divide by 3, I get 5 over 6. So these are my two critical values in radians. So I'm going to make a sign chart. Now, if you want to do your sign chart in degrees, you can. So 30, I'll just draw it down here. It's not wrong. I was just seeing if things were multiple choice, so you could match up the answers in radians, okay? That's why. And so we're only going from 0 to 2 pi. So we're not going to go on forever. So what we need to do is we're going to plug it into the derivative, which is right here. So this will take a little bit more time. I'm going to move this up. All right. We need to pick like 15 degrees. And it's not one of my special triangles, so we're going to have to logically think through if something's positive or negative. Okay? So I want to know, is negative sine of 15 degrees plus 1/2, if that's positive or negative. So let's look at sine. So sine looks like this. So let's just say this was 30. And we know that that value is 1/2. Okay. So if I take 15 degrees, I would be about right here. And so that number is less than 1/2. So I've got negative, and we'll just say it's less than 1/2. And so I just want to know, if I take negative less than 1/2, like 0.4, and I add 0.5 to it, will it be positive or negative? That's all you're trying to figure out, okay? And you do need to know this strategy because it does happen. Well, if I had negative 0.4 plus 0.5, I get a positive. And so that's how, even though I can't find that value, I can still rationalize if it's positive or negative. Then I want to pick something between 30 degrees and 150. So I always do 90 degrees because that's pi over 2. So I'm going to pick 90. So is the negative sine of pi over 2, or 90 degrees, plus 1/2. So go back to your sine. Well, at pi over 2, it's actually 1. So I get negative 1 plus 1/2. Which is negative. And then it probably will change signs because that's how cosine works. And this wasn't kind of a funky equation, but let's try 180, which is pi. So is negative sine of pi plus 1/2. So if we go to pi, we get 0. So negative 0 plus 1/2 is positive. Okay. And so we knew that our original function, this is f of x, was increasing to decreasing to increasing. Now, this one also has endpoints. Okay. So so this one's to find all local extrema. So what you notice is right here on the endpoint at 0, that is a minimum. It's a low point. So I'm going to say minimum at x equals 0. And then I get a high point. So we're going to say max. That's at pi over 6. So x equals pi over 6. Then I come down here, and that's a low point. So at 5 pi over 6, that's also a minimum. And then I stop at the end, and that's the highest point in that little area. So that's a max. So don't forget your endpoints if you have a restriction, okay? They are also local extrema, like picture here, okay? We cannot classify absolute extrema this way, so that's going to get its own section. Okay, one last example. I just thought I'd throw in a new derivative for you. So find max and min, so we're going to take our derivative. Now this one, because I have like a -1, I can just do a chain rule. So we're going to bring that down and multiply. The inside stays the same. Subtract 1, and then times the derivative of the inside, which is another power rule, so -2x. And then we're going to kind of clean this up because we need to solve it anyway. So negative times negative, 2 times 2, so 4x over 3, and then this comes down here. That's a cubed root, okay? So if we want to set this equal to 0, I'm also going to set for undefined, which is our denominator. Equal to 0. All right, so when you set this equal to 0, we're going to multiply by the denominator. We're already checking where it's undefined, so that would go away, and we get 4x equals 0, divided by 4, so x equals 0. That's a critical value. I'll just put it in the middle. I don't know what my other one is. For undefined, we'll divide by 3, so that's gone. The opposite of a cubed root is to take the third power of both sides. So I get 36 minus x squared still equals 0. Add x squared. Take the square root. And don't forget it's plus and minus 6. Okay, so all three of those are critical values where possible max and min can occur. Because this is a cubed root to start with, I don't have a domain restriction. Okay. So that's also important. That 3 means it's a cubed root. You can do negative cubed roots. If it's a square root, I would have more, I would have like part of my number line chopped off because there's a domain restriction. All right, so now we're going to test it. And you do need to test it before you've gotten rid of anything. So I'm going to just test it in here. So I'm going to try like -10. So on top, I'd have a negative. That 3 doesn't matter. So I have -10 squared is 100. 36 minus 100 is a negative number, and the cubed root is still going to stay negative. So a negative divided by negative is a positive. Then I'm going to try -1. So I would have negative on top. So -1 squared is 1. 36 minus 1 is 35. It's positive. The cubed root of a positive is a positive. Then I'll try 1. So positive. 36 minus 1 is 35. The cubed root is still positive. And then I'll try 10. So positive. 36 minus 100 is negative. Cubed root of negative is a negative. Okay. So then I don't even worry about increasing and decreasing, writing it out. So I just know my original curve is going to be, keep going. It's going to increase. We're going to decrease. We're going to increase. And then we're going to decrease. So if you are drawing this out, you want to exaggerate it so you can tell if you're getting bigger or smaller. So our final answer is we are going to, our endpoints don't matter because they're going to keep going forever, but we have a local max at here and here. So it's 6 and -6. And we have a local or relative min right here at 0. Okay. And I just want the x values. If you want the y value, you would just plug it into the original. This little note is to make sure you really do understand. If I had to justify something and I needed to declare something was a max or min or increasing, I would write out the rule in words. Okay. All right. Well, you give your Practice a try. Email me if you want a one-on-one Zoom to do any of the solving, especially the trig or review any of the derivative rules, whatever you need, okay?